এন্ট্রি দিচ্ছ অর্জুন দা?
হ্যাঁ, এন্ট্রি কি দিয়ে দিই নাকি?
হ্যাঁ দাও, 45 তো হয়ে গেছে। হ্যাঁ, বসতে অসুবিধা নেই, সেটা তো পারবেন, ততটা একটু বই করে দিয়ে বন্ধ করে খাওয়াটা বেরিয়ে যাবে। বেশ থেকে করে এসো। হ্যাঁ বলো। শুনলে শুনতে পারবি, শুনলে শুনতে পারিস। না না, এইটাই বিছানা শুলেও দেখা যাবে না। এই, বললাম বিছানায় শুলেও দেখা যাবে না।
হ্যাঁ অর্জুন, হ্যালো। হ্যালো হ্যালো শুভদীপ, হ্যালো।
বিশ্বজিৎ কোথায় গেল?
হ্যাঁ শুভদীপ।
হ্যালো, হ্যাঁ
হ্যাঁ অর্জুন,
বিশ্বজিৎ কোথায় গেল?
বিশ্বজিৎ তো আছে। ও
একটু
আবার বেরিয়ে
অডিও অফ করা।
হ্যালো। অমরিদা,
হ্যালো,
হ্যালো।
হ্যাঁ নির্মলেন্দু বলো।
হ্যাঁ শুনতে,
হ্যালো,
হ্যাঁ হ্যালো হ্যালো। না আমি শোনা যাচ্ছে কিনা আর কি,
হ্যাঁ
অর্জুন
শোনা
বা
যাচ্ছে।
শুভদীপ কারোর আওয়াজ পাচ্ছি না তাই বলছি।
হ্যাঁ হ্যাঁ হ্যাঁ, ওদের ছিল কিন্তু কোথায় গেল আবার সব?
অ্যাকচুয়ালি স্যারের খুব প্রবলেম আজকে, আজকে ওরা থাকতে পারবেন না।
ও, দেখো যতটা সম্ভব টাইমটা মেনটেন করো।
হ্যাঁ কারেক্ট টাইমে।
হ্যাঁ, টাইমটা মেনটেন করবে সবসময়।
হ্যালো অর্জুন, এর কোথায় গেল? শুভদীপ, হ্যালো।
নির্মলেন্দু দা, হ্যালো হ্যালো হ্যালো।
শুনতে পাচ্ছ শুভদীপ?
হ্যাঁ হ্যাঁ, বলছি
হ্যালো,
ইউ
হ্যাঁ।
ক্যান স্টার্ট নাও। ডিজে স্যার হ্যাজ,
ওকে,
স্যার স্যার এসে গেছেন, ডিজে স্যার এসে গেছেন।
আচ্ছা আচ্ছা। অমরিদা স্টার্ট করি তাহলে। শুভদীপ মে আই স্টার্ট?
Yes, yes, you can start now.
ওকে।
You can start now.
Hello everyone. Very good morning to all. Very welcome to all the participants for being with us in this one-day state level webinar on discovering the fascinating world of nanoscience. This webinar is a part of year-long celebration of 175th year of establishment of our esteemed institution, Krishnagar Government College. Though our college had started its journey in the year of 1846, the Department of Physics came to its existence in the year of 1880. And since then, the department with great pride and honor, has been serving the society by imparting quality education to the students. Many of them are first generation learners coming from surrounding areas. In every year, our students perform very well, and even few of them secure ranking in the university examinations. The department as a whole take pride in the fact many renowned and eminent personalities of Bengal have come to this department either as a teacher or as a student. Now, in this pandemic situation, to energize and motivate our students and also to enrich ourselves, we have organized this webinar. But why it is nanoscience? First of all, it is now a part of BSc syllabus under newly introduced CBCS system. And secondly, we are eager to give exposure to our students to a field as fascinating as nanoscience is, which has connection with almost all fields of science. Is it a new science? Though nanoscience seems to be a few new field of application, there are strong evidence that the use of nanotechnology existed in the ancient India in the form of wood steel. The Lycurgus scarf in the British Museum collection is the oldest famous application of nanoscience. Also, there are many evidence of existence of nanoparticles in nature. For example, lotus leaf, the brilliant blue color of morpho butterfly, and so many. I'm sure this webinar will motivate our students to their future endeavor. To organize this webinar, we are thankful to our respected officer in charge, Dr. Shobhan Yogi, Associate Professor in Chemistry, and IQAC Coordinator, Dr. Amoris Mondal, Associate Professor in Bengali. We cordially welcome them. We are very grateful to our honorable speakers, Professor Debnarayan Jana and Dr. Shouris Banerjee. We are very pleased to welcome them. We also cordially welcome all the participants to make this event as a success. As we received overwhelming number of registration from all over India who have arranged YouTube live streaming apart from Google Meet platform to accommodate as many participants as possible. We request all the participants to mute their microphone and video and not to share their screen. Any query about the lectures may be communicated through chat box in Google Meet or YouTube Live. Now, our honorable officer in charge, Dr. Shobhan Yogi, was supposed to give welcome address, but unfortunately, since he is not keeping well today morning, here he has sent a message, and now I am reading out this message to our audience. Message from officer in charge. Namaskar and good morning to you all present in this web platform for today's one-day state level webinar being organized by the Department of Physics, Krishnagar Government College. Today, the department along with IQAC of the college is organizing one state level webinar on discovering the fascinating world of nanoscience. Today, two senior faculty members from one of the oldest university of India will speak for a college which is also one of the oldest in the country and our state. I wholeheartedly welcome our two respected speakers of the day, Professor Debnarayan Jana, Department of Physics, University of Calcutta, and Dr. Shouris Banerjee, Associate Professor, Department of Physics, University of Calcutta. Kolkata, West Bengal. I also welcome my beloved students, my colleagues, and students and teachers from other institutes who have joined in this webinar. Krishnagar Government College is celebrating its 175th years of establishment. The grand opening program started on 27th November 2019, and we planned a lot for year-long program for this occasion. But since March 2020, as we know, the cloud of COVID-19 has stopped almost all activities of the academic world. But still, academic interactions continued with the students by various online modes. But a new opportunity of higher level of academic activity opened in front of us by using Google Meet and YouTube platforms in the name of webinars. With very sincere efforts from all of us and respected speakers who are presenting their views on various topics, has become a very valuable platform for exchange of academic ideas. I once again welcome Professor Jana, Department of Physics, and Dr. Banerjee, Associate Professor, in this webinar. Thank you. Now, thank you, sir, for your encouraging words. As always, it has been. Now, I would request our respected IQAC coordinator, Dr. Amresh Mondal, to say a few words. Please, sir.
Thank you. Thank you, Nirmalendu. Good morning, everybody. It's my privilege to have been asked to say what's in this one-day state-level webinar on discovering the fascinating world of nanoscience, organized by the Department of Physics in collaboration with the Internal Quality Assurance Cell, Krishnagar Government College. On behalf of IQAC, I would like to express my hearty congratulations to Dr. Biswajit Pal, head of the Department of Physics, and his departmental faculties, Dr. Arjun Das, Dr. Nirmalendu Hui, Dr. Subhadeep Nath, and Dr. Hiranmoy Pal for organizing. From the end of IQAC, Krishnagar Government College, I am happy to announce that we are going to organize today the webinar number 13 since last month of July 2020. It is definitely a positive approach from the side of all different departments of the college towards continuing and meeting the emphasis at this pandemic situation. I express my hearty thanks to Dr. Shobhan Yogi, officer in charge of this college, all head of the departments, and IQAC members like Dr. Kaushik Sarkar, Dr. Sutapa Sannal, Dr. Indrita Saha, Dr. Gopal Das, Dr. Sujit Ghosh for their endeavor to organize such webinars. Now, I would like to express my gratitude to our distinguished speakers, Professor Demnarayan Jana, Department of Physics, University of Calcutta, and Dr. Saurish Banerjee, Associate Professor of the Department of Physics, University of Calcutta, who have given their kind consent to deliver lectures in this webinar. From core of my heart, I believe that this webinar discussion must enlighten all the participants. I am expecting all success of today's webinar. Thank you. Thank you all.
Thank you. Thank you, Dr. Amoris Mondol, for being with us as always. Now, it's my pleasure and feel highly honored to introduce our first speaker, Professor Debnarayan Jana. Professor Debnarayan Jana completed the doctoral study from Raman Research Institute, Bangalore in 1997. In 2000, he joined the prestigious Department of Physics, University of Calcutta, as a lecturer and subsequently promoted to Professor of Physics in 2012. He is also a fellow of West Bengal Academy of Science and Technology and life member of Indian Physical Society. He was also awarded as Distinguished Scientist in Physics Award from Venus International Research Award, Chennai, in 2017. He was a visiting fellow in CCMS NTU Taiwan from 2003 to 2004. Dr. Jana worked as distinguished teacher as well as frontier researcher in both theoretical and experimental condensed matter physics. As recognition, he has awarded Tarapado Maiti Sriti Puruskar and Vidyasagar Sriti Puruskar from SSTA, an NGO from Purbo Mednipur, West Bengal, India. He had visited and delivered lectures in ICTP Italy, ETH Switzerland, CERN Switzerland, and other prestigious universities and institutes in Europe. He has more than 135 papers in national and international peer-reviewed journals and have been associated as reviewers of many reputed international journals. His current research interest is focused in defect studies in JNO, interface growth problem, nonlinear conduction in disordered systems, and density functional theory studies in carbon nanotubes, graphene, T-graphene, silicene, and germanium. Along with his distinguished collaborators, he had written 4 review articles, and one of his works in JNO published as an invited review in Procom Mat Science in 2009 is highly acclaimed by the material science researchers. With his able guidance, 12 students have already obtained PhD degree from University of Calcutta, and about 8 to 10 students are working with him to finish their PhD research work. With this short introduction, I request Professor Jana to share his expert opinion. Please, sir.
Okay, thank you. So this is my first time giving a lecture to Krishnagar Government College, and in this pandemic period, since you have arranged this webinar, so it will be very useful to the audience as well as the researchers in this drama. And I have actually this presentation into 2 parts. So in the first part, actually, I will talk about the general features relating to this nanoscience and little bit research which I am pursuing at present in Calcutta University. And the second part, I will try to show some kind of a video where this length is going from top to bottom. So hope you'll enjoy this thing. So with these brief introductions, again, I am very much worried and thankful to this audience in the sense that in this period we have been able to connect this webinar, and if there is any problem in internet connections or other things, please tell me so that we can arrange better in near future. So may I ask that is it audible to all the things, Dr. Nath, Dr. Shubhadeep Nath? Can you please tell me that whether it is audible to not? Hello, your microphone is off. So before I start.
Yes, it is audible. It is audible.
Okay. Thank you. So
Yes, you can start now.
okay, so you start now.
Yes, you can start. Audible.
Okay. So we'll start with this dimensional analysis and Nano-Science. So this is the university. I think everyone is known to this 150 years old institute. So our department actually is both in the first, second, third, and fourth floor. And I actually presume my office is the ground floor. So here is my list of research interests and the collaborators which I am pursuing my research. On the right hand side, I have the students and the latest updates. They are actually performing the research in abroad also, and you'll be happy to know that Dr. Subhadeep Nath is also working from your college with me for last few years. So you might think that in near future you might start working on this particular field so that you can start working in the nano field directly. So although I have given you a representations of different areas in my physics, but mostly I am concerned with the second thing, that is the density functional theory in different 2D material systems, as you have already advertised in noting down my short biodata. So, but I am also working on kind of experimental project related to zinc oxide, and there are many types of defects that to arise in this oxide semiconductor, and it is interesting to share with you that although these topics are quite 3 decades old, however, there are kind of various new kind of path-breaking problem to arise in this zinc oxide time to time. So still, I will say that there are few problems which are there in zinc oxide. Still, we do not understand completely till date. So with these things, I have planned my talk in the first few slides. I will go to some applications of dimensional analysis to uncommon problems. Then I will go directly to the most important part, that is the dimensional analysis nanoscience, and I will slowly give my conclusions on this talk. So you might have heard these two lines many times, but it's always interesting to quote these two famous Nobel laureate scientists, Dirac and Fermi, who says that the physical laws should have mathematical beauty. And Fermi says that those who really understand the nature of a given phenomena must obtain the basic laws from dimensional consideration. So as you know that although this dimensional analysis is included even in the school, colleges, in the beginning of your physics courses, however, it was not properly either utilized or given a kind of preference to understand the basic physics in a diverse system. So in my few slides, I try to give you some kind of presentation where this dimensional analysis can be very useful, and I will presumably after this talk you will try to understand some of the features which you have already known through your basic physics course. You can use this kind of concept so that you can understand it much more clearly. So with this thing, let me give you a kind of a very simple theorem which you already known in class 7 and 8. That's the first kind theory, that's the Pythagorean theorem. So it can be proved in many ways. Here I'm showing a kind of a cartoon picture, symmetric cartoon picture, where you can actually feel the sum of this area, right? So you can actually cut the paper in a such way that you can fold it in many ways to show that the area is remaining constant. So with these things, let me try to picturize this simple theorem. How can you prove this Pythagorean theorem through dimensional analysis? So in this slide, I'm trying to show a kind of right angle triangle, and I have drawn a kind of perpendicular to it, and then I have divided this angle and this area into two parts, that is A1 and A2. So by its very definition, the area must be only the length square, because the M, L, T, M and T power will be vanishing this zero, and you can write down a functional dependence on some kind of dimensional number theta, which have been included in this particular triangle theta, and then you can write down this total area of this right angle triangle as the sum of these two areas A1 and A2. And once you write down this functional dependence f theta into a square, and then f theta equal to c square and f theta equal to b square, this f theta will cancel out from the both sides. So we finally obtain that the square of the hypotenuse as the sum of the other sides, square of the other two sides. So this is a very well-known proof, and which have been there in a kind of literature, but I feel that this has not been taught in a better way. And I leave it to you, to the audience and the students, that instead of thinking f theta, can we think of other two angles, that this f theta could be depending upon the other angle phi. So if f theta phi is there, if phi another angle is included is there, will this proof will go on to be valid or not? I leave it to you to think about it, and also to think about, suppose instead of kind of a planar triangle, if I would like to draw a triangle on a kind of curved surface, something like a on the surface of a balloon, floated balloon. So try to think it that whether this law, that is c square equal to a square plus b square, will be valid or not. So with these two questions, I move into the next slide. That this is another interesting phenomena, that there are no small animals in the polar region. Why is it so? So this can be understood in the basis of this given analysis by noting down that this heat loss must be proportional to the surface area and the mass, which is also proportional to the volume. So if you calculate the heat loss per mass, this will be area divided by volume. So this is the area inverse. So if you try to look at this, that is most kind of animals which are observed in a kind of polar regime is basically a kind of a large kind of a number, that is large animal, not small animal. So if you now calculate this thing for a mouse which is of the order of 5 centimeter, you find out this 1 upon n is very small, or 20, and this polar bear which is 2 meter, that is very small. So if you take this ratio, that is 40:1. So it is not possible for a mouse to survive on the basis of this heat loss per mass. That is, it will lose heat at least 40 times higher than a bear, so that it will never be survive in that particular diverse area. So that's the precise reason behind why mouse does not exist in the polar region. Why I am actually telling this feature, because we'll see, and subsequently will be shown by Dr. Banerjee in the next lecture, that this nanoparticle, also this surface to volume ratio, is playing an important key role. So there are many active cells which have been adsorbed. So this ratio actually forms a fundamental key factor in understanding the diverse applications of nanoscience. So that's why I've included this thing. So you also have understood that Gulliver Travel problem, because he was there in the Lilliputian, so it was 12 times higher. Is it like a simple gossip like of story, or is it kind of a real true story? You can argue that this the mass dependence and the volume dependence is exactly like the similar thing, because the intake of a person needs to be proportional to the volume and proportional to the mass, and we have shown that it is the linear dimension cube that is important. So if you think about that, whether they will be able to provide such amount of food, whether it can enter, then you can find it out, it is almost impossible to be a kind of survival in that thing. So this is just like a I can say a story, not like a real phenomena. So this also can be understood by this basic argument. So this is another simple dimensional argument, which is the following. You must have, I think, heard this problem, and you have solved this problem in your class 10 geography chapter, where you are supposed to calculate what is the mass of a largest stone that can be moved by a flowing river. How does it depend upon the velocity, density of the stone and the acceleration due to gravity? So you must have seen that the mass which can be carried, it depends upon the velocity, sixth power. So how does this sixth power come? That can be understood by simply writing down this simple dimensional analysis, that mass will depend upon the velocity. So you equate the both sides power of m and l and b, and finally you come to the conclusion that the maximum mass which can be carried by a flowing river depends on the sixth power of the velocity of the river. So this is a very interesting thing, which is not open. Again, I am telling you, exercise in the kind of or understanding a problem. So it is not like a problem which is to be from a physics. It is basically the science problem. You try to understand certain problems by simple writing down this spatial dependence on few parameters, and then can write down immediately. This is another problem which you have come across in your BSc first year exam or first year syllabus on the general properties of matter. This is called the Newtonian flow of liquid to a tube. So how does it depend on the radius of the tube as well as the length of the tube? You can find out there are kind of few dimensionless kind of quantity which I have listed out, and this is the radius, this is the length, this is the pressure, and the coefficient of viscosity. So you can find out the rate of flow of liquid depends upon this nice pattern. But if you can think of like this rate as a kind of ratio of the pressure gradient, you'll find out that ddt, that is the rate of flow, depend upon this pi r to the power 4 into theta into L. And the exact formula which you have carried over and reduced it, you must have seen that ddt is equal to pi p r to the power 4 by 8 theta L. Of course, this pi by 8 being dimensionless number will not be able to derive from this thing. So it is the claim of dimensionality to how to write down the appropriate parameter. By the way, on the passing comment is that our blood flow in our vessel, in our body, did not obey this Newtonian motions, but they are actually non-Newtonian liquid. But of course, part of this analysis might be important to that thing. So we use here a Newtonian assumption, not the non-Newtonian assumption, to calculate, let's say, flow of water to a tube. This is another interesting application of dimensional analysis. That is the how to understand Stephen's law in a black body radiation. We know that we are also black body because we are in the infrared region. So how do you understand this black body? Black body is nothing but a body which is in thermal equilibrium with the surrounding. Along, it must satisfy so-called the Planck radiation law. So in that kind of definition, you must agree with me that you are also a black body, and our body temperature satisfies the green displacement law. So the question is, can we understand this different law by simply writing down this dependence that E by V is called the energy density. So energy per unit volume. So particularly d-dimensional system, this energy is m L square T minus 2 divided by m to the power d, because d-dimensional volume must be proportional to m to the power d. And if you identify being a quantum phenomena, there must be Planck's constant, and being a photon, this is a relativistic, so that speed of light should be there, and being a thermal equilibrium, temperature must be there. So given this information in your hand, you can now writing down this dependence x, y, z and solve this equation x, y, z, and you can find it out. Find out this Stephen's law does indeed depend upon the arbitrary spatial dimensions, and in your odd 3-dimensional world, this is exactly t plus 1, that is, it is t to the power 4. So in 2 dimensions, this should be power should be t cube. In 1 dimension, this should be t square. So this is the natural way you can actually calculate this dependence of the Stephen's law in arbitrary space D. Okay, so this is another kind of problem from fluid dynamics. So this is the Navier-Stokes equation. So you try to calculate what are the drag forces, speed of the cone. To make a cone like this thing, you ask the following question: that if you change this length scale, do you think how does their terminal velocity will be there? So you can identify that kind of two forces. Remember, this viscosity is known as the kinematic viscosity, that is the viscosity divided by the density. That's a very common kind of viscosity terminal when you discuss the kind of fluid dynamics. So you can find it out that you can find out two independent dimensional groups and writing down this equation. Then you find out surprisingly when this drag force is equal to the weight, you find out this velocity terminal depends upon this quantity. So all cones, if they are made up of the same kind of paper quality, they are kind of the dimension will not come into the picture at all. So 1 meter, 2 meter, which was advertised in the previous slide, both will come or receive the same terminal. There's a very interesting result which can be derived by the simple dimensional. So this is all about the simple introduction to the dimensional space, to the natural physical problem. Now we are entering to the nanoscience, and where nature finishes producing its own species, man begins teaching natural things, and with the help of this nature, create an infinity of species. This is a quotation from Leonardo da Vinci. So, is it this nanoscience known to this thing? Why nanoscience is so important? Because nanoscience is that particular branch of science where atomic physics converges with the physics and chemistry of complex systems. So the two milestones of our physical science, that is quantum mechanics and the statistical mechanics, will come into the future, and there could be different varieties of features which are coming slowly one by one. So it is basically, truly speaking, multidisciplinary or interdisciplinary science. It is connected to the different varieties of science, including the conventional science. So in this science, slide, I have shown you that it is related to the chemistry, physics, material science, colloidal science, bioscience, and the various branches of engineering. Not only the usual engineering, mechanical, electrical, but the computer science is also very important, because the structure designing before you start any experiment or kind of prediction, it is necessary to simulate that particular nanomaterials and try to look out whether it possesses certain interesting, important physical properties. So the history of nanomaterials goes back to 4th century of AD. There are kind of Leica curve which looks different color in reflection as well as transmission. There is these Damascus blades which are used in the famous sword of Tipu Sultan, and whoever is interested must visit this Srirangapatnam of Mysore, South India, and please can touch this sword. It is kept there, and you feel it how it is there, still there. And those who are also traveling to Ajanta caves, you find out this painting which were made with the curable nanomaterial. Even in the Ayurvedic medicine, the gold nanoparticles are used. So it is not that the recent time people know it. It has been discovered, rediscovered many times. So even the gold nanoparticles, I will show you that to change its color if you change the dimension of the system. Here I have shown you that if gold silver nanoparticles are there, that is 70 nanometers, then this color is like this. This is completely different from the usual golden color of gold. So let me start with these simple features of these atoms. You must have noted down this Bohr model, And we know that with the nucleus there are kind of protons and neutrons and electrons are there in the outermost orbit. So the question is, what is the size of the atom? This can be easily understood by writing down this kinetic energy by the uncertainty relation, which is given by this h cross square by 2mr, and the potential energy is the Coulomb energy. And then if you try to minimize this total energy, you come back that there must be a minimum of this total energy. So here is this kinetic energy plot shown by this blue curve, and the potential energy curve is shown by the red color, and the total energy which is shown by this black color. You find out there is a kind of negative uh, potential energy, total energy is a particular value of this thing. This shows that there is a minimum of this core radius. Okay, it's a very simple way of understanding this thing without going details of the Bohr model. It also illustrates another interesting feature that the velocity associated with any Bohr orbit should not exceed the speed of light according to the special theory of relativity. And if you actually show that thing, then you'll find out that this atomic number Z must be less than a fine structure constant, that is h squared by h+3. So you know that you cannot have a kind of any stable atom which atomic number should be exceeding 137. That's a very interesting result coming directly from the dimensional change. So if you look out this dimensional features more than, you find out this here is basically of your 0.1 millimeter. So this is 100 micrometer, and if you convert this into the nanometer, 100,000 nanometer. So 1 nanometer, you must remember that is 10 to the power minus 9 meters. So if you think of the kind of a daily life, you will find out how much kind of nail is increasing per second. That is actually a simple scale of nanometer. So here is a closer look to a human hair, and this speed line is 100 nanometers. So look at this picture which has been taken from this typical closer look to a characterizing instrument. So what is meant by this nanoparticles? So nanoparticles are the particles, that's the standard definition, 1 nanometer to 100 nanometer. This is a very accepted definition, but I should say 1 to 50 nanometer is better. So 1 nanometer means there must be 5 to 3 atoms. So it is almost 40,000 times smaller than the width. So here is a scale of different nanometer scale, that is size of the hydrogen atom, size of the protein. Your computer chip is 180 nanometer. However, this diameter of this human hair is 10 micrometer. So why do we bother about this nanometer? Because we show that in the nanoscale, the physical, chemical, biological, all these properties will be different from the bulk property. Here is a kind of a slide which shows these things which are available in the nature and which are man-made. So right hand side, different scales are there. You can find it out. So this is a kind of a compact features of this thing. So let me move into the future slides. So there, what I told you earlier, that this bulk gold appears yellow in color, but the nano-size gold, which is not yellow. So this changes color. So why this is changing color? This can be understood because the particles are so small. So they are actually confined to something like a particle in a box model in quantum mechanics. So the electrons are not free to move as they are were in the bulk gold. So once this movement is restricted, so they will differently react with light. So if you have a confinement of the particle in a box, you know that there will be discrete energy levels available, and these discrete energy levels can tell you that what kind of wavelength of color will be emitted by this particle. So here is this another interesting feature associated with this nanoparticle, that's called the surface area to volume, which I told in the beginning of the slide. So if you take a kind of a cube of size 1 millimeter, its radius, its area, there are 6 areas, so area must be 6 square meters. Now you divide it into the half of on the surface. You remember there all this surface area reduced it half of meter square, but the number of surface areas that actually increases. So when you multiply this thing, you will find out the surface area 6 into half meter square into 8. You further divide it by 1/3 of this thing, although it is reducing, again the number of cubes which are attaching to this different surface that increases to 27. So you look at this from the ball counterpart, the area is increasing like this thing. So the surface area of our volume is shown here in this graph, that how is it changing with the particle size. So this is very important whenever some catalytic, photocatalytic or adsorption phenomena is there. This phenomena of this attaching to many number of particles into a given area, that's very important. So this reactions is important for this surface area. So here is that which I told you, that particle in a box. If you change this dimension of the particle size, the color actually changes. So here I have shown you this, there is a quantum dots. Dots means it is like artificial atoms having few number of electrons in a typical size, 3.2 nanometers in diameter. It will show this blue emission. If you have a 5 nanometer, so it will have red emission. So all these things is that we are changing the small this L square values in this diameter size. So that's why there are different colors. So here all the effect of this quantum size effect, that which is very important in designing different material which can change this the band gap. So we can see that this band gap actually is changed by two terms. One is that 1 upon r squared, that is called quantum five confinement, and the second term it is the Coulomb term, which is depending upon 1 upon r. So you can see that this from the bulk property, when you have this semiconductor or the nanoparticle semiconductor property, you can see that this band gap changes like this pattern. So this band gap tuning is a very important phenomena in our nanomaterial research. So we try to tune this band gap. We're trying to reduce or increase this band gap as required by different mechanisms. We could apply electric field, we could add some functional kind of functional radicals, or you can change the different atom position. There are many ways. You can also apply some strain and all these things that can change the band gap. So here is another phenomena of natural, that is which was already told in the beginning, that is called the lotus effect. Because you know this, a lotus generally is seen to grow in muddy rivers and lakes. However, their flower and the leaves are completely clean. The self-cleansing property is very important. So this can be understood in the level of so-called the surface tension in the nanometric regime. And actually this natural phenomena has now been taken care in the kind of typical paint which can be seen to develop this self-cleansing property. Here is a view graph of computer graphics of lotus leaf, and here is another property of nanomaterial called super repellent. You can see that this is not actually attracted, completely repellent. So again, has to tailor with the surface intersurface tension and controlling these things. There are kind of many view graphs of these things. That's why this self-repellent property is there. So now I'm going to this the work which I'm doing for my research, that is the different carbon material. So here is the slideshow of carbon, various material, that is called the zero dimensional, that is called fullerene, 60 carbon molecules here, they are sometimes called buckable. This is carbon nanotubes, which is called 1D, quasi one dimensional, and this is called graphene, which has been awarded the Nobel Prize in 2004, and this is a bulb, that is called the graphite, which has been seen in your pencil. So these are actually connected by van der Waals interaction. So that's why you can write it. And this particular interaction is important for future designing of material. So here is this carbon nanotubes basics. So this is actually a long nanotubes where it can be used by different means. So I am showing a kind of computer graphics where this is rotating, and this has been actually discovered by Ijima, the Japanese physicist, Ijima, MEC department. So these are actually empty cylinders which can be rolled up as a sheets of single and several concentric layers of graphene. I'm showing in the next slide that there are two ways you can do it. That take a graphene sheet, These are the unit vectors of the honeycomb cell, and there is a chiral vector C which have been denoted by this vector and the angle. And if you take a roll of this graphene sheet, that's like a taking a plain sheet, then you roll it, you find out you have obtained a carbon nanotube. So rolled graphene sheet, you'll find out this carbon nanotubes of a particular diameter. And this carbon nanotube has interesting property, as I have been shown. There are two numbers N and M which are connected by these two unit vectors A1 and A2. These are called the integers, and you will find out depending on these values of N and M, you can have various flavors of carbon nanotubes starting from a metallic to semiconductor to insulating. So N minus M, if it is actually divisible by Ti, then you can have a kind of a typical metallic or a small blanket that is called semi-metallic, or a kind of by T times integer the semiconducting property. For example, we'll see that several nanotypes, you take this 8 0 nanotubes, if 8 minus 0 divided by 3, this is not divisible by 3 integer, this is fraction, so this is semiconductor. But if you take 6 6, this is a metal. If you take 6 0, that is called quadrimetal, because 6 minus 6 is 0, both are divisible by 3. So we actually study all these kind of 2D materials or kind of any material cells, material by a universal kind of theory called the density function theory. So this is basically a theory where we look not in terms of the wave function, which is a very common feature, but by kind of a density. So this is very useful for computers to do that thing, and for this thing, the Nobel Prize in Chemistry was given to Sir Walter Kohn with Popper in 1998. So here is a self-consistent approach in DFT. You guess a kind of density, then you plug this density in this particular energy functional with kinetic energy, potential energy, and other terms, and then you can. This is the handle of this exchange force. This is very important, and you have to guess that which particular exchange correlation is important. So these parts are almost fixed. Here is this your intuition. All this will go to this particular feature, and you guess these things. If you integrated about this density over this total space, you get this total number of electrons, and then you find out. And then you find out this trial error, a trial density. Then you again put this trial density, run this thing. So there is a self-consistent feature of self-consistent in the ground state density and ground state energy. So you plug into that particular electron density where there is no change in your energy so far. So a brief history of DFT is that already DFT was noted down. It was known to the nuclear physicists who are using Thomas Fermi theory in condensed matter theory, but it was not already till date, this 1960 and 65. So where this really modern DFT begins with Kohn-Simon equation by introducing these orbitals, and 99% of the time they are right, and you obtain then this local density approximation, which is a wonderful approximation in your DFT, and the gradient approximation were introduced 1965, but it took almost few years, that is 25 to 30 years, to develop the appropriate code for this thing. That is 1993 and 1998, as I told you, Kohn and Popper win the Nobel Prize. So from 90s decade and till date, it is now wonderfully used by many people, and some of these softwares are free into the internet. You can start uploading and downloading these things and check your calculation. So here is a computer generated content YouTube, and this is by our basic definition, the metallic thing. So we have to design this chip first, and then you try to change this speed, you try to apply electric field, and you can actually sheet out, clear out this carbon atom. This is very actually tough to clear it out, because these carbon atoms are bonded with the two carbon atoms. Very tough to do this. This is another simulation of this rotation of this carbon nanotubes. Again, the 1010. So you can do this simulation with the help of appropriate software, and then you do this DFT density function. So let me the next few slides I'm showing you, I will come back to this story of nanoscience in a minute. But let me show you few of the works which I've been doing in the last few years. That is the graphene sheet. Here you must have seen there are different sides. So the sides which are denoted by position A, C, and D, E, and where this other position SC1, SC2, these are two different positions. So on A, C, these are called so-called the equivalent position, and other things are called the non-equivalent position. Okay, so these are A, C, right? This D, these are equivalent position, but C1, D1, Q1, F1, D1, these are called non-equivalent position. And if you try to calculate this deformation energy, you can find out that after this is all these things are same. So here is a change in band gap. As I have told you, if you don't this some of these carbon atoms by boron and nitrogen, you find out that there is a change in band gap. So this is the work which I started with my student Palasnath, which they are in college. So this is the first paper from our group on carbon on the DFT calculation of graphene, and this paper is quite well cited. And 2017 or 18, this work was experimentally verified. That was also appeared in carbon. So here is another constant change in band gap of this graphene nanotube. If you attach this nanotube, you'll find out there is a crossing of these bands. So that is called semi-metallic valence band and conduction band. But there is also opening of band gap that is also known as semiconductor. So it depends upon how you attach and how many number of these nanoribbons you attach. That will change the band gap of the system. This is another work which I have done with my student who is going to write it. This is Arko Bandhopadhyay, and then Autoru and Orunangola, which was there at Children University. This was published in Physical, Chemical, and Chemical Physics in 2017. This is the structure where you use some kind of a flux to change the flux of this associated ring and look out the band gap of the ring. So this can be done by a tight binding model, and this tight binding model also can give rise to the same polar beta. So armed with both the tight binding calculation along with DFT result, we can generate band gap structure and other. This is one of the recent work which we have predicted another two-dimensional carbon allotrope where this carbon 4-ring, 5-ring, and 8-ring simultaneously present. So we have shown this band structure, and this material shows some kind of negative differentiation. You know, this negative differentiation is a very common phenomena in our particular this quantum mechanical tunnel diode, right? So this differential resistance shows this IV, del I, del V. So there is a region where it shows this negative differential resistance. Also, this can be very good for a lithium and sulfur battery as the encapsulator of cathode, because cathode most of the time it is actually damaged. So you can use this as an encapsulator. Again, this is a theoretical work which has been published. This is by the Frame and myself. So this is another paper which has been also published, and Dr. Subodhip Nath is there associated with this particular work, where we have used basically tight binding model to calculate and show the robustness and the topology of Dirac cones, and this is an analytical work which has been duly supported by the density function. So what we do in nanoscale is actually it can be doing in many ways. So here is a chart where we have shown the how is it related to various things. So you start with simulation and then predict some results. Then there is kind of synthesis and characterization. Then you start out some kind of application and then fabrication. So this is the way we actually do the research on the nanoscale. Okay. So here is a slide where we show how the property of this nanomaterial changes from the bulk feature to as you decrease the size of the system, that is 3D to 2D to 1D to 0D. So 3D, it is well known to you that the density of state goes as 5 to D, and 2D is like a staircase, and then constantly staircase, and this 1D, this is called the band of singularity, it goes as 1 upon 5 to D, and the zero dimensional quantum dot, this is actually given by kind of a delta function. And it is really nice to share that this particular theoretical predictions have been experimentally verified by a group in Cultivation of Science, Professor Bhupen Dev's group a few years back, which have been published in PGIE. Exactly the similar feature which have been seen in experiment 2. So this technology also can be used to reduce the size, where it can change the storage capacity. We have shown that it will change this size. As you can see, this capacity of storage also will be changed by 1,000 times. So you look at this, the previous storage media which was CD and DVD, now it can be storage up to terabytes. And now I'm going slowly to some of these applications which can be told again by most clearly by my next colleague, Dr. Banerjee. And here it is, I'm using these quantum dots to how it can be used to detect some kind of a tumor in a particular early detection mode. So if you insert some kind of quantum dot of a particular size, they are capable of generating some ultraviolet light. By finding different ultraviolet light of different dimensions, you can actually look at the kind of typical tumor size that can be. So this is already done in kind of mouse, and now it is almost they have to check the immunity. There is again another mouse having to detect this colon cancer by iron oxide nanoparticles, which can be seen by this structure. So this is another interesting effect for the enhanced permeability tension, abbreviated for EPR. So normally the blood vessels which are there, they are not leaky under the new to normal condition. But if you have a kind of a tumor in the blood vessels, they are quite leaky. So you can actually inject the appropriate size of things to enter that thing and block that thing for the property. This is very important intravenous administration of these particles, which can actually cure this problem due to the effect of the blood. So here is some kind of the references of these people who are interested to start and learn in the beginning. So this might help you. So while showing you this few of these, there are many more of these things in the internet. You can search it and find out. But I find these 5 are quite basics. This is the famous book by Krishnagar and Gross, and you can start and then you can learn it. So I'm showing my group members here at present working the postdoctoral fellow, Dr. Sumana Sinha, and he has submitted and waiting for the and these are my next group of students who have or submit the thesis in this year, and these are my junior research fellows which are going to submit. So with that thing, I will conclude, and this is a book which has been published from this Lambert. If you are interested, you can see some of these practical applications of dimension analysis of modern perspective. And I will thank you, and I will show another slide which is there to show the dimensional changes. So please wait for a few minutes. হ্যালো, 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 শুভদীপ, ক্যান ইউ হিয়ার মি?
হ্যালো হ্যালো
দেখা যাচ্ছে না, দেখা যাচ্ছে না?
হ্যাঁ দেখা যাচ্ছে
হচ্ছে, পরপর
দেখা
হচ্ছে?
যাচ্ছে হ্যাঁ হচ্ছে
ঠিক আছে, থ্যাংক ইউ।
হচ্ছে কত দূরে গেলে কি হয় সঙ্গে কিছু নেই
Okay, thank you.
Thank you, sir. Thank you, sir, for this wonderful and enriching talk and the wonderful video. This talk will surely help our students to understand the relative dimension of the materials and what is nanoscience. The main question is that they will motivate. This will also motivate the students to the future endeavor. So even though this presentation is self-explanatory, there are few questions which the participants has asked in the Google Meet and YouTube platform. So
Okay. Okay.
So I am asking one by one. So, is there any structural deformity in the nanostructure like the nanotube and the 2D nanosheet with the change
Yes.
of temperature? And if there is, so how can we overcome it?
Last part, I cannot hear it. The last part.
Yes. How can you
Temperature
overcome how can you overcome the deformation due to the temperature in the nanotube or 2D nanostructures?
There are kind of, I think there could be core cell structures or there could be another sheet which can actually protect this thing. So this is a kind of a covered sheet. I think Dr. Banerjee will tell more detail about this thermal stability of the different nanostructures. Okay. So you can use some core cells type of structure, another sheet. Okay. Next.
Okay. Next is there are similar type of 2 or 3 questions. There's what is zero dimension or what is quantum dot? Like
the quantum dot I told you, I think Dr. Banerjee also will tell you, this is an artificial atom which can contain few number of atoms. Okay, 2 to 3 atoms confined in a region, that is called a quantum dot. Okay.
And what is zero dimension?
Zero dimension means that it is point-like object. Okay, so it has 3 outer dimensions, point-like object. So this is although mathematically viable, but we have been able to, in a nanometer scale, we have been able to point out these certain objects which are called zero dimensional objects. In the mathematical sense, it might have been a kind of zero dimension. How is it feasible? But it's like a point object, point in that scale, where all the other dimensions are fixed. Okay.
So next question: how nanoclusters differs in their selectivity towards absorption based on their shapes and edges?
This is a very good question, no doubt. But shape and edge is an important parameter in the nanosheet and nanoribbon, because these shapes actually change the topology of the structure and in the absorbing area. So you can absorb different types of hydrogen precipitates or different kind of area by appropriately cutting with this nanoribbon. So shape actually changes this absorbing area as well as the typical magnetic state of the system. So that's why one can change this thing. But there is not kind of hard and fast rule. One has to do this numerical computation and then find it out.
There is another question that nanotubes are most studied material because of its potential of doing better than other standard silicon or germanium-based devices that we have now.
Right.
Now the question is, are we getting the results of these nanomaterials in its application in electronics devices or so?
So
and is there
I think I understand the point. Although actually it started with a very fascinating color, carbon nanotube. Actually, transistor have been used. This red kind of transistor has been already used. There are other kind of particular adsorption like platinum adsorptions also that can be also used experimentally and surface area kind of changing. And mostly this conductivity, thermal conductivity, thermal stability, and also this current carrying property, that is important. So you can control both in the upper side and the lower side. That is the surface. And another interesting thing which was proposed that elastic constant was quite high. However, most of the cases what we found out that you cannot make prepare very long carbon nanotubes. So all these carbon nanotubes are shorter in size. So that is actually preventing us to make a very sophisticated and longer carbon nanotubes. So that's why this research in carbon nanotubes has not been done in that particular area, which have been done in case of graphene and other 2D materials. So now the more fascinating one is that rather than this quasi-online. So that was there, I think, in the from 96 to 2001, 2004, like that. And most of the cases, what happened is that the multi-wall carbon nanotubes also is prepared very easily in the synthesis, but very difficult to do simulation. Whereas single wall carbon nanotubes is not difficult to do computer simulation, but it is very difficult to separate from other things. There are techniques, electrophoresis, and you can separate the carbon nanotubes of different flavors.
Okay, sir. Two more questions.
Okay.
How many atom was taken in the calculation of graphene? I think in the DFT.
This depends upon the larger supercells, how can you produce. Okay, so it depends upon your computer thing. But most of the cases, if you take 2 to 3 small unit cells, that will give you generally a at least understandable result, but not publishable in the format. You have to take appropriate number of atoms, such as this band structure and other things are very smooth enough.
Okay. Okay, sir. And how much industrially successful is nanotechnology? How much industrially successful is nanotechnology? I think
Industrial, right?
Industrial.
I think industrial, right? There are many kind of successful applications. I think next speaker will tell more about it. At least in the cosmetics, this has been quite used. Zinc oxide nano powder has been used as a cosmetic. You must have seen the players like cricket players have been using to protect UV the skin itself. That is the zinc oxide nanoparticles. Then there are also many more applications in paints also. Titanium oxide nanoparticles have been used to such that this dust will not adhere to the surface. So there are many more even in the industrial applications are there. So both in the biomedical section, biomedicals as well as industrial, many more applications are there, and people are trying more.
Okay, sir. Thank you. Someone is asking for some reference books on this nanoparticles and quantum dots.
Yeah, that's a thing because there is not a single book. You have to actually download several books. Maybe I list it next time. If somebody can send me an email, I can give you the list. Okay,
Yes,
not a single book. One more thing is that for CBCS new courses, we are actually writing a book, and this will be published in the next month. But that is only for the course structure. If you would like to know more than that, there are many varieties. Suppose you would like to know only the practical application, and somebody wants to know the synthesis part, somebody wants to know the simulation part. So it is not possible till date that one book will cover all these things. So it has been seen that people who are working is truly multi-dimensional work.
yes.
So whoever working in a synthesis, so synthesis part will be more than that any other part. So who are experimentally, they will not talk about the computer simulation DFT at all. So we are trying at least one part of it is already in the published in the next month. I think. So this is for the BSc course, newly introduced BSc course. So hopefully you will enjoy that book, and maybe in the near future we can have a better one.
Okay, sir. Okay, sir. Thank you for this enriching talk and for giving us the valuable time.
Okay, and I thank you all the faculty members of your college and for arranging this talk. And thing is that I have taken some more time, so I'm sorry. I should finish it by 12.
Okay. It's a very
So I think
it's a very good
the next speaker.
interesting talk.
Okay, so the next speaker can now enter.
Yes. Yes, sir. Now,
Okay.
so thank you, Professor Jana. Now we are moving to our next session. Now I am privileged and feel pleasure to introduce our next speaker, Dr. Shourish Banerjee, Associate Professor of University of Calcutta, who will talk about the experimental aspects of nanomaterials, its way to synthesis, its characterization, properties, and application. Dr. Banerjee obtained his PhD degree from Indian Institute of Indian Association for Cultivation of Science, Jadavpur University in 1998 in experimental material physics under guidance of Professor Dipankar Chakraborty, SARC Distinguished Fellow and INSA Honorary Scientist. He then joined Bangladeshi College, Kolkata as lecturer in physics in 1999. In 2000, he joined the Department of Physics, University of Calcutta as lecturer. Now he is posted as an associate professor in physics, University of Calcutta. He has teaching experience of 21 years, while he is attached to active research for more than 27 years altogether. His research interests include synthesis and characterization of nanomaterials, synthesis and characterization of double perovskite systems. He has over 70 publications in national and international journals and conference proceedings to his credit. He has guided 6 PhD students, out of which 4 have been awarded degree. So now I welcome Dr. Banerjee for his talk. So sir, it's over to you now. Sir, can you hear me?
Yes,
Yes, it's now over to you.
yes. Okay, let's start my talk, the experimental aspects of nanomaterials. Is it audible?
Yes,
Can you hear me?
yes, it is audible. We can hear you.
Okay.
We can hear you.
So this is the roadmap of nanoscale. We start from a size of a baseball bat, and then it reaches to the dimension of the DNA, which is of the order of nanometer. So from the baseball bat size to the fingertip, this is the 2 orders of magnitude decrease. That is its size is of the order of 1 centimeter. From the fingertip to the middle eye, it is the 1 order of magnitude decrease. And from middle eye to human hair is also 1 order of magnitude decrease. Up to this, you can see by your naked eye. But in order to see the structures beyond that, you have to take the help of some powerful microscope. So blood cell, which is a dimension of the 10 micrometer, bacteria, which is a dimension of 1 micrometer, and this is our coronavirus. This has the dimension of 100 nanometer, and that finally reached the size of the DNA, 1 nanometer. So from the baseball bat size at the order of 1 meter to the DNA, this is actually 10 to the power 9 orders of magnitude decrease. And finally, we reach to the nanometer size. Now, in the year 1959, Professor Richard Feynman delivered his famous talk, "There is plenty of room at the bottom," indicating that there is an immense scope of miniaturization of the material, and his vision was to write the 24 volumes of Encyclopedia Britannica on the head of a pin. And the present nanotechnology has almost fulfilled the concept of this miniaturization. So, if I compare this, the first point contact transistor built in 1947 with the modern Intel chip that contains 1.9 billion transistors, you can actually get the progress of this miniaturization. Then there is a law that is called the Moore's law, after the Gordon Moore, who actually predicted that the number of transistors over a single integrated circuit that will double in every 18 months. The advantage of this is the reduction of cost and size of these devices, and also the packing density that will be immensely increased, and that will consume less amount of power. The devices will be faster with the increasing clock speed. Now we are dealing with the different material. There is the single crystalline material or polycrystalline material. The single crystal material has the dimension of the order of millimeter to centimeter, and the polycrystalline grain size of the order of micron. In contrast, the atom size is of the order of angstrom. Say the hydrogen boat radius is 0.529 angstrom. And nanomaterial, that is the nanoscale, that is within the two extreme size regime, that is the atom regime and that of the macro regime. So all these properties are structure sensitive, and that will be also different from that of the atoms and also balls. And there are several examples of nanostructure in nature. That is in the form of the carbon black that contains the fluorines and carbon nanotubes in the mixed phase, and also the medieval artists unknowingly used metal nanoparticles to get the bright colors of the church windows. And butterfly wings that contains the photonic crystal that shows a diffraction effect, and that is responsible for the brilliant colors. And if you can have the nano projection under the slits that will help them to cling over the smooth surface. And lotus leaf that is covered with some hydrophobic waxy material that is of the order of nanometer dimension, which gives the self-cleaning property of that material. And molluscs create nectar that is the composite of this polysaccharide chitin and the calcium carbonate that is in the stacked fashion, so that the transverse crack cannot propagate within the material, and this shows a highest amount of material strength, that is a Young's modulus of the order of 70 gigapascal. And most side that contains the nanostructure hexagonal elements, and that is the low has the low reflectivity, and that will help them to see under a very low light. And these nanostructures are prepared in the laboratories. There are some examples. This is the branched gold nanoparticles, and this is the zinc oxide in the form of nanoring, nanospiral, and nanostring. There is several silver nanostructures also seen is in the form of cubes, bars, nanoprism, and pyramids, flowers, and the spheres. Now, we cannot see these nanostructures by your naked eye, so we have to use some powerful microscopy. So these are some examples of microscopy used to visualize these nanostructures. This is the transmission electron microscope and the high resolution transmission electron microscope that uses the transmission electron beam, and the field emission scanning electron microscope, that is the EPSEN, that contains the scanning electron beam. The scanning tunneling microscope, that is the STM, that maps the tunneling current between the conducting tube and the substrate, and that can be reflected as the topography of the sample. And the atomic force microscopy that uses the atomic force, and that is finally presented as the topography of the material. Now, one can estimate the particle size by a routine analysis using the X-ray diffraction pattern, and that can be easily done in the laboratory. And from the line profile analysis, you can calculate the average particle size. Now, these nanostructures can be classified in three categories. That is the two-dimensional nanostructures, one-dimensional nanostructure, and zero-dimensional nanostructures. And two-dimensional nanostructures, along with the size of the that is of the order of nanometer, they should have some confinement of the charge carriers. In case of three-dimensional system, the electrons and holes in case of semiconductor can move freely in three directions. But you have to confine this system in a strategically so that it can move along some particular direction. In case of two-dimensional nanostructures, this confinement appears along a particular direction, and these carriers are free to move along the perpendicular direction. That is the over a sheet. So these examples are there quantum OL, two-dimensional superlattice, and the graphene. In case of one-dimensional nanostructure, the charge carriers are allowed to move along a particular direction and confined to move along the transverse direction. That is the nanowire, quantum wire, or singular multi-world carbon nanotubes. And for zero-dimensional system, the confinement appears from all three directions. That is the nanoparticle and quantum dots are the examples. And this confinement arises from the mismatching of the potentials, and that is offered at the surface of this nano regime. And this, as this structure is in between the atom scale and that of the macro scale, so it can be prepared from the either direction. You can there are two definite process of preparation method, that is the top-down method and also the bottom-up approach. Now, for the top-down method, you actually start from a macro structure and purposefully carve it and just result to a particular structure. In case of bottom-up approach, you start from a atom or molecule and restrict the growth up to a certain extent. And the nanomaterials contains this limited number of atoms. That is of the order of 10 to the power 3 to 10 to the power 5 number of atoms. And that is very less compared to the Avogadro number. Now, this is a synthesis procedure for the colloidal gold nanoparticle. This is one example of the bottom-up method. So, for the precursor material, we use the chloroauric acid and the sodium citrate. Sodium citrate is added dropwise in the chloroauric acid at some elevated temperature, and that results to the gold nanoparticle. That is of the order of 50 nanometer. Also, the size of this nanoparticle can be maintained or tuned by application of the capping agent, which is sometimes called the surfactant. And these are actually some organic molecule which attacks the nanoparticle surface and restricts the growth somewhere. Now, for the isotropic capping, that results to the spherical nanoparticle. If this capping is anisotropic, that means that if the capping agent actually attacks at some definite surfaces of the crystals, that the selective growth is appeared, and that results to the high aspect ratio material, which is the nanorod or the nanowire. And this is the ball milling approach, which is the top-down approach. We start from a material of the dimension of the micrometer or the powder and place this material within some grinding jar. The grinding that rotates along some distance. Suppose it is rotated in an anti-clockwise direction, and all these grinding jars are placed over the fan wheel, which rotates along the clockwise direction. So this direction of rotation is actually opposite with respect to each other. And each of these systems that results to some centrifugal force, and the combination of these two centrifugal force that results to the Coriolis force. And due to this Coriolis force, the balls within this jar have some trajectory that moves some half circle, then it make impact over the wall. Now, between the collision of this of balls and due to the impact, the powders are crushed to the nanometer dimension. The particle size can be controlled by the ball mass ratio, milling duration, and the size of the ball. And this mechanochemical reaction can also be done. Actually, the reactions which are actually not applied, not possible thermodynamically, that can be also done by these impact forces. Now, this is the sol gel method. You can also prepare this nanoparticle by this sol gel method. Here, you take the metal alkoxide. This the metal is the silicon, zirconium, or titanium that contains the alkyl group. This methyl group or the ethyl group. So the structure is like this. The monomer has the structure MOR like this. So, for example, the metal ethoxide of silicon is the tetraethyl orthosilicate. This is the silicon has the 4 bonds. Then it has the formula of the SiO2H5 4. So OC2H5 group is actually attached to the one silicon atom. This is the monomer. And in presence of some pH of the medium, that is, if the medium is acidic, that the reaction promotes. With the environment of water, that group is hydrolyzed, and that forms the hydrolysis reaction. And when this system is stirred within a beaker, this produces a clear sol, which is the actually colloidal suspension of alkoxide and a solvated metal precursor. Then this is allowed to be settled in a particular petri dish, and that results to the water condensation, where water molecules are produced, and the alcohol condensation results. And the subsequent process, the network formation continues. And network formation, that means the bridging oxygen between these uh, metal atoms will be produced, and that somewhere percolates, and the viscosity of the medium suddenly rises, and this becomes a semi-solid material, and this is called the gel material. And that gel contains the some amount of liquid, that is in the form of water or alcohol, etc. And when the evaporation continues, that forms the finally network formation, and there should have some pores within the material. And depending on the pH or temperature, nature of the catalyst and the water cation molecular ratio, you can result the different type of materials from this solvent process. So this is one sort of thing. Is the fiber is extracted. It can be extracted. Then gel can be prepared in the form of the zero gel. That uh, shows the this is the zero gel that produces the crack within the material, and that results this type of structure. And this is another thing. This is the aerogel that contains the lot amount of pores. And finally, you can put this uh, sol over a some substrate that can be done with the deep coating, spray coating, or the spin coating method, and you get the film material. So you can get these particles, monolace, fibers, and films out of this in the solving process. And this metal salts can be added uh, during the salt formation, and finally, when it is heated, that can be result to the uh, metal oxide nanoparticle. Suppose I take the copper nitrate and it is mixed with the salt, and that results to the when you heat the material, that is after gelation, when you heat the material, that results to the formation of the copper oxide nanoparticle, and that is coated by this silica matrix. If I take the tetrahedral orthosilicate as the precursor material. Now, two-dimensional nanostructures or two-dimensional nanosheets can be prepared within the sodium core mica as a template material. Now, this is the composition of the sodium core mica that contains magnesium, oxygen, fluorine, silicon, aluminum, sodium, etc. And sodium, that is the core sodium ions per unit cell, that is loosely attached to the oxygen ion. And this is actually the alternate structure of channels and blocks, and this channel width is of the order of 0.6 nanometer. These channels can be explored to construct the two-dimensional nanosheet. Now, first of all, the metal ions are exchanged with the sodium ion, and then subsequently the chemical reaction is done. For example, hydrogen gas, if it is subjected to the hydrogen gas at the elevated temperature, that is it's 700 degree Kelvin, for example, that results to the sulfide nanosheet. Or you can prepare this with the metals and nitrides as well of the dimension of the 0.6 nanometer. And another template is the porous alumina. This contains some that carries a lot of amount of surface energy that confers its optical, electronic, and the magnetic properties. And some unusual properties can also result. And the bulk periodicity is may not be hold in case of nanoparticles. That means the band structure can be modulated. Now, as I mentioned, and then as I mentioned that there should have some confinement effect. Let's play with this confinement in case of zero-dimensional system. There is a spherical particle having the radius a, and the potential is very large at the surface, r equal to a. There is a hard potential, and that particles cannot come out of this system. So there is spherical symmetry that wave function is the radial part and also the angular part. The radial part can be given by the spherical Bessel function. That spherical Bessel function has this some property that shows actually the different zeros. This is actually red card is a J0. So 0th spherical Bessel function that goes as sin x by x. Okay. But all other values, this is the green J1, this is the green card, green dotted card that shows this type of functional dependence, and J2 this type of dependence. They are passes through this origin, and each of these type of Bessel function that shows some zeros. These zeros appear for the J0 type of spherical Bessel function, and for this G1 or etc. Now, from these zeros, you can calculate this that wave function should also vary at this boundary. This boundary at r equal to a. And that means that you can calculate this energy eigenvalue from this system. So that goes as 1 by r square, 1 by a square rather, just as a particle in a box problem, one-dimensional box problem, inverse square of length and inverse of mass, but it contains a factor that is the ZNL, that may not be an integer quantity, may be a fractional quantity. Okay, these are the actually position of zeros. For L equal to 0 is the first zero, second zero, third zero, and so on and so forth, and L equal to 1 less. And L's are indexed as the different different sub levels. That is the 1s, 1p, 1d. If I arrange this in the from the increasing manner, that results to this type of energy variation. In contrast to the Coulomb potential, that shows this type of progression. So this I can say that the energy levels are quantized. If I consider now a semiconductor system in the bulk and the other the nanoform. In case of semiconductor, this is the conduction band and a sort of the valence band. And this is a band edge at the conduction band, and this band edge also in the valence band. And now these energy levels are actually splitted. So the minimum energy for transition for the bulk is the from the valence band top to the conduction band bottom, that rises to the energy band gap, bulk band gap Eg. But in case of nanoparticle, that transition is from the 1sh to the 1se. That is obviously larger than that of the bulk band gap. So that means the energy gap in case of nanoparticle is enhanced. But in case of our system, we are not dealing with the single electron or single hole. There is lots of electron and holes. So you have to define some length scale with respect to which we can define some confinement. That is called the excitonic ratios. Then the exciton in the bulk semiconductor can be defined as the coupled electron and hole system found by the Coulomb attraction that is moving through a crystal with same group velocity, and that forms a bound state. Due to the formation of this bound state, there are several discrete energy levels within the band gap. So the transition may now appear from this valence band to the first excitonic level, to the second excitonic, third excitonic level. So you can see the different peaks Also, the transition may appear from the valence band to the conduction band. That represents the band edge. So before this band edge, you get this several peaks, and these are called the excitonic peaks. And the excitons in case of semiconductor, which are weakly bound exciton, can be represented as some hot wire type of exciton. And they follow the hydrogenic system and comprises of the effective electron mass and effective whole mass that moves some center of mass system, and that is placed in the material having the dielectric constant epsilon, that is of the order of 10 in case of semiconductor material. So due to the presence of this, excitonic energy levels are defined by this formula, which is in contrast to the hydrogenic system, which is this minus 13.6 divided by n square in PV. So in case of hydrogenic system, you get the binding energy, that is 13.6 electron volt. But in case of, due to the presence of this value of epsilon and also the value of mu, that is much less compared to the 3 electron mass, that energy levels are squeezed. So you can get this binding energy of the order of milli electron volt, which is much less compared to the phonon energy at the room temperature. So as the phonon energy is much higher, then excitons will not exist at the room temperature. In order to see the excitonic behavior, you have to perform the experiment at a low temperature. So in case of due to the low amount, this amount of low binding energy also associated with the excitonic Bohr radius, which is of the order of several lattice constants. Now this is an optical absorption study where we use this spectrophotometer arrangement where you take a light source. This is a white light source containing all the spectrum, and this is incident on the diffraction grating. The diffraction grating disperses it, and you get a dispersion of the spectrum. And when this grating is rotated, the spectrum is shifted with respect to the exit slit, and that is incident on a sample material, and the intensity, outgoing intensity, is recorded with the help of some photomultiplier tube or some electronic detector. So this is actually exit intensity I. Now when the incident intensity, you replace the sample and you record this incident intensity. Obviously, there's due to some absorption, the exit intensity will be lower compared to that of the incident intensity by this formula. So this D is a sample thickness. That sample is kept within a particular quartz cell, and from this you can get this alpha. This is the absorption coefficient of this material. Now, in case of gallium arsenide system, this is actually the typical absorption graph for different photon energy. The gallium arsenide system is a delayed bandgap semiconductor having the bandgap energy 1.43 electron volt at room temperature, and that varies as shows this type of power law variation to the power half for the direct bandgap system. And you see there as the temperature variation of the absorption coefficient, and it is shifted from the higher energy scale to the lower energy scale due to and the excitonic peaks also shifted along with it. So this is actually trend. The variation is like this. This shows the absorption age beyond 1.43, around 1.43 electron volt. You get the maximum absorption, and these excitonic peaks are just appears just below the absorption age. That at the high temperature, the phonons will collide with this exciton, so the peak heights will be decreased, and that result to the flattening of the peak. And finally, at the room temperature, there is no peak. Now, this quantum confinement defines in the three things. That is the one is the excitonic Bohr radius, and is the electron Bohr radius, and the hole Bohr radius, and the particle size. The particle size, that strength of the confinement will be given on the where this particle size is placed on this inequality. If this is very small compared to the all other things, that means that it gets the strong confinement. Or in this case, you get the weak confinement, and then for intermediate confinement, you have to keep it within the electronic bore radius or the hole bore radius. So, in this is actually the calculation that is done by Eli Brass, and this is by the effective based on the effective medium theory, and the calculation is results that the energy required for the electron from travel from the valence band to the conduction band is like this. So in case of bulk, there is only the band gap energy Eg, but here you have the here you have all in all cases you have the some energy added to the system. This is actually confinement energy. That confinement energy that is strong in case of particles if the particle size is very small. That means the in case of in this system R is very small compared to the other systems, and also the mu, that is the effective reduced mass of the electron and hole, that is also least. That results to the high value of confinement. Therefore, band gap modulation is done in this sense. In case of weak confinement, this is actually the transitional mass. This is the total mass of the electron and hole, and the radius is also higher compared to this, so that results in the less amount of contribution. And this contribution arises from the Coulomb interaction and the polarization energy. This is the less amount of contribution over the exciton energy. So what we get actually the band gap will also increase in case of nanoparticle system. That means that you get a blue shift of the absorption edge. The absorption edge will shifted to the blue end of the spectrum. Also, you get the different feature in along in the different confinement regime. Okay. Now, this absorption or emission process is actually the cumulative effect of the nanoparticles. As actually all the particles are not monodispersed. There should have some size distribution. Generally, it is the log normal distribution or the Gaussian distribution. That depends on the process parameter of the material, and also that also sensitive to the shape of the material and the impurities and the surface contribution. So you won't get this type of discrete behavior, though it is theoretically predicted, and we call this sometimes theoretically we call this as a due to this discrete energy level, we call this as a artificial atom, but it is not usually practiced. But you can see, you can get the flavor of this thing when you perform the single dot spectroscopy. So you detect a single atom, a single nanoparticle over a substrate, and excite that single nanoparticle, and record the emission spectra. And from this, you get some behavior. There's one sort of things is the fluorescent blinking. Is the nanoparticles do not excite in a continuous manner, but it causes blinking. These are two states are given. One is the off state, and another is on state, and another is the off state. And this is the detail of the some optical absorption study of the cadmium selenide nanoparticle. Here you get the some distinct exciton peaks. The particle size is varied from 1.2 nanometer to 11.5 nanometer. You actually see the excitonic peaks actually vanishes as this particle size is increased. So that means that you are moving from the strong confinement regime to the weak confinement regime. As the absorption age also shifted as the particle size is changing. Actually, 250 nanometer absorption age shift is done in this process. Now, this is that actually cadmium selenide nanoparticles contains within some container which are excited by ultraviolet radiation. The particle size is the emission of this material. The particle size increases along this direction, and particle size is maximum for that emits the red color, and the blue color that has the minimum size. So this that can be represented as a quantum rainbow. And this color of this can be varied by the particle size variation, or we can tune it by adding some activated atom in the material. So pure zinc sulfide that emits at the 344 nanometer, if it is activated by the manganese atom, that produces the emission at the 590 nanometer with the enhanced efficiency, and that is controlled by this oscillator strain. Now, these nanoparticles that contains these oscillators can be factor, this U0, that varies as the AEX divided by R particle radius with the cube form. So this enhancement of luminescence appears due to the reduction of this particle size. So that means the electron and holes are confined within a short region, within a limited region. The overlapping of these two wave functions, electron and hole wave function, is maximum. That results to the maximum amount of luminescence, and that can be applied to the some display devices. And this is the variation of density of states in case of low-dimensional system. In case of three-dimensional system, that shows as or half type of variation, density of states. In case of two-dimensional system, with the formation of the different subbands, they get the staircase-like variation. This is actually shown by this equation. And in case of one-dimensional system, that shows some spike-like variation of density of states. For the zero-dimensional system, this shows in case of one-dimensional system, that shows some inverse square root of dependence, and in case of zero-dimensional system, that shows as delta function like behavior. And electronic and optical properties are controlled by this density of states of the system. And for example, quantized conduction is seen in case of one-dimensional system due to the particular feature of this density of states in case of one-dimensional system. Now, IC industry has used these lithographic techniques where the ultraviolet radiation or the optical radiation is used for the photolithography. This incident of the photomask that selectively allows the radiation to pass through it over a photoresist material, which is a polymer material, and that reacts with the incident reaction, and that have shown some differential solubility with respect to some solvent. And finally, you get the you can prepare different windows, and where you can dope some materials purposefully to get the diode, transistors, gates, MOSFETs, etc. in this structure. Now, the reduction of this structure size is limited with the radiation used. Now, as you want to reduce the structure size, you have to reduce the wavelength of radiation. Otherwise, diffraction effect will blur the structures. Now, this conventionally, the radiation used in case of IC industries is the krypton fluoride, argon fluoride, and fluorine laser. That beyond that wavelength, that wavelength, and beyond that wavelength, that radiation cannot be controlled. So, how can I do if I want to reduce the structure size? One thing is the use of electron beam lithography. That is, the differently wave of the electron is taken into account, which is of the order of fraction of angstrom, that can be tuned by the accelerating voltage. And as this wavelength is small compared to the structure size, so you can reduce the structure size compared to the previous IC design. And that can be focused over a lens, focused by the electromagnetic lens system, and that can be deflected easily over the surface. So, using some pattern generator, you can construct the desired structures with high packing density. So let me show you some example of the electron beam lithography with reactive ion etching. This can generate this nanostructure from the top-down approach. First of all, a two-dimensional nanostructure is prepared by molecular beam epitaxy or MOCVD. Now, next, a resist material compatible to the electron beam is deposited over it, and the electron beam is scanned over the surface that uh, breaks the bonds of this polymer material at the particular location, and uh, it can be etched out with some particular solvent like ethyl isobutyl ketone, this type of solvent, and rest of the photoresist is intact. Finally, metal is deposited over the surface. So in this position, metal is over the bare semiconductor surface, but here this metal is over the photoresist material. Then by the lift-off technique, you remove the metal and the photoresist material over this region, but the metal covered over the semiconductor surface remains intact. So next time you use the reactive ions as a reactive ion bombardment by the reactive ion etching process. The metal covered over the semiconductor surface protects this with respect to the reactive ion, but the rest of the positions or portions are actually etched out, and you get the some nanostructure formation over this material, and that can be uh, that can show some reproducibility, some excellent reproducibility. And can also prepare some arrays. You can change the shapes by just patterning the scanning area, etc. Now, atom manipulation can also be done by scanning probe microscopy. So, one thing is scanning probe microscope is the scanning tunneling microscope, where it registers the tunneling current between the conducting tip and the conducting substrate. The tunneling current varies exponentially with the separation. So the sensitivity of this microscope relies at the factor that is varies exponentially with this distance. By mapping this tunneling current, you can get the topograph of the uh, sample material. This is actually STM image of the platinum 111 surface. Now, it can be used of the manipulation, atom manipulation process. So, the some adsorbate atom, that is those atoms which we want to manipulate, are dispersed over the surface. In the imaging mode, that uh, atoms are actually recorded, and as the tip separation, now the tunneling current is increased, so this tip separation between the uh, adsorbate atom and that of the tip is decreased. And by applying some voltage of the order of 10 volt, you can get the uh, inhomogeneous electric field. It's a highly inhomogeneous electric field just below that of the tip. This is the actually electric field map below the tip, and that actually uh, induces the dipole moment. That dipole moment produces the potential variation. So this periodic potential of atom is now modified by presence of the electric field, and that shows some global minimum. And this adsorbate atom is now just placed uh, below this tip, uh, reaching at the global minimum. And this finally this tip is moved, and that adsorbate atom also move slides over the surface, and a particular location. When I decrease the tunneling current, the tip will also be shifted upward, and that is imaging mode is presented. So this is some example of the STM manipulated structure. This is the first shown by the Igler. By writing 35 xenon atom and designing the tiniest advertisement of his company, and it's the poral arrangement of the iron over the copper one surface in a circular manner. This is another example of the thing, that is uh, the coral is presented over some elliptical arrangement of the cobalt atom over copper surface with the different eccentricities. Atom scale resolution mask can be prepared. Suppose we take first the hydrogenated silicon surface, and now I purposefully mm, remove the hydrogen atom at some location of the silicon atom and place some another atom at the particular location. Okay. Now the molecular level chemical reaction can also be done by this atom manipulation method. Here the reaction is done over the two iodobenzene molecule that results to the one biphenyl. The 1.5 electron volt tunneling electron actually breaks the bond between the iodine and the benzene ring, and next the two benzene rings are brought close together, and that results to the biphenyl. And these are some applications of this nanotechnology. This is the hydrophobic coating that is actually seen in the lotus leaf. That is that coating of the nanoparticles has sprayed or painted over some surfaces, this type of different surfaces, and that systems are immune with respect to water, dust, dirt, oil, breeze, etc. There is a company which is branded name of Namo. They have prepared this type of shirt and that is immune with respect to all these things. Now, Nano-Science titanium dioxide or the zinc oxide uh, used for the cosmetics, and they have the reflecting power in ultraviolet rays, and that nanoparticles and the carbon nanotypes can be used as nanomedicine. They can be used as delivery of drugs directly to the affected human cell without disturbing the normal cells. Medical implants can be done with respect to nanozirconiums, which are the biocorrosion resistance and biocompatible. Nanosilicon carbides at the best candidate for the artificial heart valves, and presently artificial retina is can be used as this graphene implant. Zinc selenide, zinc sulfide, cadmium sulfide, lead telluride that can be used as a next generation light emitting phosphorus. Carbon nanotubes can be used as the field emitters in the field emission display. And the graphene is the thinnest material that has the maximum amount of transparency at 98% over wide wavelength range, and that can be used as a flexicon or the transparent display. As the nanoparticles contains the large surface area, so they contains the more amount of energy, and this is used in the battery, can be used in the battery industry. So nickel metal hydride batteries that made nanocrystalline nickel and metal carbohydrates that can be that is used for with less frequent recharging, and that will last for longer time. Aircrafts made from the bucky paper, that is the lightweight with low fuel consumption. And graphene can be used as a filter for the particular type of atoms, particular type of molecules. Suppose graphene oxide can be used as a water filtration and desalination process. Okay, thank you. So,
Thank you, sir. Thank you, sir, for your talk on the experimental aspects of nanometers and its application. This talk is really motivating, and it will motivate the students in the emerging field of nanoscience. and it will be really enrich the student participants to the experimental synthesis of nanomaterials and its application and its characterization, etc. So, sir, we have few questions from the participants. So, can I proceed?
Okay.
Okay. So, so how much has India improved in the nanotechnology? You have shown some applications. I think has India really has proceeded, has improved in the applications of nanotechnology?
Actually, some amount of research fundings are there, and they are using some some nanotechnology field. Suppose they have used in case of some coating materials or some nano cosmetic materials, etc.
Okay, sir. So another question is, what are synthetic nanoparticles?
Actually, these nanoparticles which we have prepared in the laboratory, these are actually they are synthesized in but depending on some process parameter. Uh, Actually, we want to mimic some aspect of the nanomaterials from nature. Suppose the Lotus leaf effect that is used in for the coating over the glass material, so that water droplet cannot be over that material. So these are all the synthetic nanomaterial that can be prepared in by tuning some parameters.
Okay, sir. Thank you. Another question is, can you comment on the relative advantage or disadvantage of nanomaterials synthesis or preparation by different techniques? You told about two different techniques, the top-down or down-up approach. So there are different techniques. What are the relative advantage and disadvantage of this method?
So several methods have some limitations also. In case of suppose the chemical synthesis method, it's a tabletop experiment. You can easily prepare a large amount of material, but the size distribution is a key factor. And this, as the particle size controls every property of the material, that is not uh, particularly reflected or tuned in that fashion. But you can prepare the material in a large amount. But in case of bottom-up, top-down approach, the process is slow, and you can prepare a less amount of material, but they have some good reproducibility.
Okay, sir. So another question is, what can you explain the transparent display?
Okay,
What is about
there is the graphene which I have mentioned. The graphene that is says that is saying that the 80% of transparency, and that can be used as a display material, and that transparency, the transmission coefficient, uh, that is over the wide wavelength range. What we use for the other type of coatings like titanium oxide, etc., or zinc oxide coating, which has some wavelength dependence, but it is actually wavelength independent. And this is the highest value of transparency, the 80% of transparency. So that can be used as a display device, some optical device.
Thank you, sir. I think there are no more questions from the Google Meet or YouTube. Okay. Thank you, sir, again. So
Okay.
we have nearly come to the end of our webinar organized by the Department of Physics KGC. We thank both the honorable speaker for giving us their valuable time with their expert opinion. Remembering the words of Richard Feynman, there's plenty of room at the bottom. We hope that the student participants can learn and motivate themselves to find plenty of room in this emerging field of nanoscience. Now I request Dr. Bishwajit Pal, Assistant Professor and Head of the Department of Physics, Krishnagar Government College, to give the vote of thanks and finally conclude the webinar. Dr. Bishwajit Pal, are you there? Dr. Bishwajit Pal.
hear me?
Yes, I can hear you. Yes, yes. You can continue now. Yes, we can. Yes, you can.
So,
Yes, Dr. Bishwajit Pal, you can continue.
we are almost fine.
Yes, there is some problem. There is some technical problem.
Behind.
No sound.
There is no sound, I think. Dr. Bishwajit Pal, we cannot hear you.
Especially it will enlighten our students in their futures.
I think there is some technical problem, so we cannot hear Dr. Bishwajit Pal. Bishwajit Pal, Dr. Bishwajit Pal, can you hear me? Okay, I think there is
No
some.
sound.
I think there is some technical problem from the Bishwajit Pal. So I will request to Dr. Arjun Das to give the vote of thanks. Arjun Das, are you there?
Yes, I am there.
Yes, you so kindly please conclude the session by giving the vote of thanks.
Okay, thank you, Subhadeep. Due to the technical glitch, our head of the department could not complete his vote of thanks. Okay, good afternoon, everyone. We are almost at the end of our e-seminar on discovering the fascinating world of Nano-Science. So firstly, we thank our two eminent resource persons. Thank you, Professor Jana, for delivering the physics behind the nanoparticles in terms of dimension analysis. And we think such a motivating presentation will enrich our audience. Especially, it will enlighten our students in their future study and research work. We also cordially thank Dr. Banerjee for his presentation on experimental aspects of nanomaterials in lucid manner. And we think this will also motivate our students toward advanced experimental research in their near future. So we think our webinar is successful to reach our goal of enhancing the motivation of students toward research work and advanced study. We are thankful to Dr. Shobhan Yogi, officer in charge of our college, who has constantly inspired us to arrange for such kind of motivating seminar that will also charge up the students in their present situation. So thank you, sir. We are also thankful to Dr. Amresh Mondal, IQAC coordinator of our college, who guided us to arrange this seminar and helped us to sketch the program schedule. So again, thanks to Dr. Amresh Mondal. And we are grateful to Dr. Kaushik Sarkar, Assistant Professor, Department of Physiology, for his technical support by sharing his great experience on video conference via Google Meet and YouTube Live. We are thankful to Arjun Das, Assistant Professor in Physics, for executing the technical part, including registration of the participants and monitoring the Google Meet. Hardly thanks to joint conveners Nirmalendra Hui and Dr. Subhadeep Nath, Assistant Professor, Department of Physics, for their constant effort to make seminar success in all respects. We convey our great thanks to all the participants for showing their interest in the seminar and their patience to make the seminar successful. We also congratulate all the faculty members and non-teaching staff members of our college for being with us. Once again, we express our sincere thanks and gratitude to both speakers and hope we will get their helping hands in future as well. And we also thank our HOD, Vishwajit Paul for his constant support and taking the permission of our honorable officer in charge. I conclude this webinar here. Thank you all. Swadip, should we conclude this session now?
Yes, we can conclude now. So hope we will be back again with webinars. We will
And all
organize
the
in
participants, please note that the feedback form is live now. You please fill up the same, and we will send you back the certificate within a few days. Okay, thank you.
Thank you.
Okay, thank you all. Please switch on the system.
Okay.
Hello. It is raining here, so the signal
Please
is
switch off
disturbing.
the system. বিশ্বজিৎ, আমি শোভনদা বলছি, ওটা অর্জুন বলে দিয়েছে।
Thank you. Thank you.
ফর্মালি ওভার হয়ে গেছে। হ্যাঁ, ওকে অর্জুন and Krishnendu, please switch off the systems, YouTube and Meet.